So I'm going to talk about the process of going from a dirty silicon wafer to a complex structure that is the crystal silicon solar cell. So our first step is to clean the wafer. So when it comes in from the manufacturer, it's dirty. It has a bunch of organic and ionic contamination, and it also has oxide around it. So we need to strip all of that off. So we have to transfer the wafers out of the manufacturing package into a carrier that is easy to handle. These things are going to be in some dangerous chemicals, so we use long handles to pick up the blue carriers. All the processes were done in this wet bench. It has a lot of baths that we can put different solutions in, and then we immerse the wafers in these baths. After everything is clean, we dry them out in this little spin dryer. Another reason to use a special carrier because it fits in the machine. And here's all of our clean wafers. You can actually see there's a flat edge right here, and each wafer has a flat edge on it. And these indicate the crystal direction of the wafer, so you want to cut parallel to that line. And it also tells you where to place your pliers every time you pick up the wafer, because every time you touch it with your pliers, or not your pliers, but your tweezers, it contaminates the wafer. So you want to do it in the same spot every time. Next, we need to grow some oxide. The oxide is just rust, like on a car frame. It's the material reacting with the atmosphere. We grew a calculated thickness around the entire wafer. We put the wafers in a high-temperature tube furnace. And there was a bubbler setup which pumped water vapor into the furnace. So moist, hot air causes the oxide, or rust. If you didn't use this bubbler, the process would be much slower. The furnace is very hot, so you have to use a long glass rod to push the wafers in. And a lot of the stuff is glass, like the carrier that the wafers is on was made completely out of glass, and it even had little glass wheels. Once they're done, you'll have a distinct color change. The color can actually indicate the thickness of the oxide, or you could use a tool called an ellipsometer to measure the thickness more precisely. You want your solar cell to absorb light, so putting little tiny holes in the device allows the light to kind of get stuck in the device. Kind of think of it like how carpet dampens sound, or it absorbs it. First, we had to clear out some of the oxide. So we do it with this mask here, or it's a pattern that we want to apply to our silicon wafer. You have to apply a coating of this plasticky substance called photoresist. We did that with this device here called a spin coater. It spins really fast while you apply your chemicals. Here's a wafer with some photoresist applied. You want it to be as even as possible. This wafer here specifically looks pretty good, except for bits on the right, it looks a little inconsistent. You want it to be a consistent bullseye pattern. Next, we apply this mask with a mask aligner, and it's basically just a bright UV light, and the photoresist reacts with UV light. Then next we need to put the wafer in a developer and then some acid to eat away the oxide, and we're left with this wafer here with our pattern etched into it. Now we apply the micropores. We basically use the same process except with a different mask. This mask specifically was made out of quartz because of how small the pores are. Here's a photoresist applied to the wafer with the tiny holes impressed in it. And we weren't sure if the mask applied properly, so we had to take a good look at it under the microscope. There are individual holes, so we figured it should be good. We used this machine to dry etch the pores. If we used acid, it would etch the sides of the pores in addition to etching downwards. The walls between the pores would likely be eaten away, leaving no pores at all. The system uses a plasma with different gases to get different effects. One gas etches, and another grows a plastic on the side of the pores. This method also applies in a single direction, So it's perfect for this application, and it's called the Bosch process. After the pores are applied, it has this holographic look to it. In order for solar cells to function, at least in terms of crystal silicon solar cells, you need a p-n junction. The silicon we were using was already p-type, so we have to dope the top part of the device with N. To do this, we applied our N-type dopant to the wafer using a spin coater. And then it goes into the tube furnace. The heat causes the dopant to diffuse or get sucked into the silicon. Now, in order to interface with the device, we need high conductivity contacts on the top and bottom. First, we did the bottom contact, which is aluminum. We apply it to the entire back of the wafer. This machine uses a plasma that sweeps across the entire silicon wafer. The plasma emits from this aluminum source, and it carries little bits of the aluminum with it. This bombards and sticks to the silicon wafer. So here's a silicon wafer that's been completely coated in aluminum. You can notice that there's a bit of a defect on the bottom right, and that wafer was likely not dried perfectly after the previous clean. To really lock the aluminum in, we place it in a rapid thermal annealer. This diffuses the aluminum into the device a bit, creating a strong electrical contact. Lastly, we need to apply our top contact. We want this contact to have a small size because it will prevent light from getting to our device. But we also want it to be large in order to have a low resistance, so it's kind of an engineering trade-off. We use the same technique as before to apply our top contact mask, but this time we have to make sure our top contacts are applied in the right spot. To do this, we have to tilt and move the mask until our alignment markers are perfectly lined up and straight. This is what our applied mask for the top contacts look like. And then we apply the gold. It applies over the entire wafer, but you have to remember that it's also applied on top of our photoresist mask. And so we use acetone to dissolve the photoresist, and it pulls away all the gold that's attached to it, so that leaves us with just gold on our contact area. And here's our devices with the top contacts applied. Our last processing step is to cut up the devices on this dicing saw. It can be programmed to automatically cut the exact dimensions of your devices. And now we take our devices to the test bench and apply a voltage across the terminals and measure the current. We do that in the complete dark and then with a light applied. And sure enough, we observe that there's extra current produced when there is light applied. So here's our finished device. And that's a 1,000 overfoot view of how it's made. Obviously, industry scales this process up, and it's all done with robots, but the processing steps are exactly the same.